Hi, welcome to lesson 36. In this lesson, we're going to just touch at the very beginning basics of modeling. And modeling is where we take your knowledge of algebra and we apply it to data. And so hopefully you already have a good sense of what parent functions look like. Okay, and we're going to get started with that idea in the very beginning. For example, maybe you plot data and this is what the plot looks like. And so you start pondering that, thinking, well, you know, what kind of graph did I have in algebra that kind of looks like that? And see, what I see going on here is kind of along the x-axis, a little bit of growth, and then we have pretty strong growth. You know, so when I look at that curve, I start thinking, oh, you know, that kind of looks like that exponential function, you know? And the exponential function is y is equal to a to the x for the very basic. And by the way, I'm not putting any slides on it, you know, left and right or up and down translations. So as I look at this, I think, you know, all of my exponential graphs went through that point 0, 1. And if I also want to pick as an important point to hit 1, 3, then I might say y is equal to 3 to the x. Because you see, if I let x be 1, 3 to the first, it would give me that order pair. Now, by the way, this is not doing the actual regressions that our technology will give us. We're going to look at that here in this lesson as well. This is just kind of doing a little bit of a curve fitting based upon our real basic understanding of the functions. Okay? And if I was actually going to use this as a model for my data, I would probably want to try some of these other values and see if that's a good fit or if I need to adjust it. Okay? Next set of data. Well, as I look at that and I think, it's kind of doing an S curve, I realize that's not exponential. It doesn't look linear. So as you look at that graph, what you might start to remember is that it kind of looks like a power function, which is y equals x to the n. And you might remember when we talked about these power functions that if n is odd, they tend to make this S curve shape. And if n is even, they tend to make the U shape, kind of like a parabola. So to me, this kind of looks like it's a power function with an odd exponent. So I'm thinking, okay, I have y equals x raised to some odd power. And if I want to use the 2, 8, I think, well, 2 to the third is 8. So maybe y equals x cubed would be a good fit for this particular data. Okay? Next guy. Well, as you look, and this almost looks like he's trying to curve back, but we're going to assume that that was just a little bit of an off value, and that it kind of does this, that it's getting real close to the y-axis, but it looks like the domain is supposed to be positive numbers only, goes through 1, 0, and then makes this wicked curve off there to the right. This reminds me of our buddy logarithms. Now, if you are really good with your logs, you realize that I can, in essence, set this up for any base I want. If I know change of base formula and all this kind of stuff. But because I want to use this 0.31, how about y equals log base 3 of x? This should have been an x, not a b. And if I put in a 3 for x, I do get a 1 out for y, so that might be a possible model for this particular data set. Now, I will say that we don't use them that much in this particular course, but you do find many, many good applications of logarithms in some of your science classes. Last guy here kind of looks like a big U, doesn't he? If you see this outside behavior, kind of looks like this, and so you think, oh, well, that's one of those power functions, and n needs to be even. Your first thought might be, how about this, x squared? That makes the U shape, but if I put in a 2, 2 squared is not 16, so you might say, well, now there are other ways I could adjust for that, but what if I do this? 2 raised to the 4th power is 16. So this is a possibility just based upon the basic shape and these two values on the graph. If you wanted to test and see if that's good, you could check out some of the other values, see how well they work. All right? So the first thing that I want you to do is to be able to recognize your basic parent functions. Okay? Now, you might want to pause this and read all of this because this is about the data that we're going to look at, so you have an idea of what we're doing. So we're talking about baseball players, and we have the height in centimeter. Now, I just took, it said about, we were also taking BMI into account. This is just for the players with the lower BMI. And the BMI value and the height was when they were playing baseball. And then we have the lifespan of those players. I don't know who collected this data, but you know baseball. They write down stats on everything, okay? So anyhow, this is height versus lifespan. And what you notice about it is that there seems to be a little bit of a downward trend, which makes you think that apparently the taller you are, maybe the shorter the lifespan. And it looks like a straight line might not be a terrible idea for a model. You know, the idea of a regression line. Although here I'm not doing a regression line, I'm doing a fitted line. So what I did is I'm in Algebra and I put a line in. We're going to write the equation of this line. To write the equation of your line, you need 2 points. So I decided that the line seemed to fit the data best if I went through point E and point H. Okay, so I'm giving you those 2 coordinates. Now, you've been writing equations of lines for a long time. You know the first thing we find is the slope. So my slope would be y value minus y value divided by x value minus x value, which equals, what's that going to be, 2.4 divided by -8, which would be a negative 0.3 if I did my arithmetic right. And you know, once you get your slope, you have a couple of options for writing your equation. I really like point slope. So I would pick one of these 2 points. It makes no difference. I'll take point E, and I'll say y minus the y coordinate is equal to the slope times x minus the x coordinate. Now this is the point slope, and some of you don't necessarily like that. You would go a different route. But then I can distribute and clean this up, and the equation that I get in slope-intercept form is y is equal to negative 0.3x plus 118.4. And we could stop and talk about what the slope means in this case and what the y-intercept means, and how useful is this model as we extrapolate beyond the data. That would be going past these values, or when we interpolate internally there. Okay. Well, going on, what I'd like to do is look at another set of data, and this is real data. It happened to be the number of women candidates for the U.S. Congress in the years, and you want to pick this up, since 1970. So in our table, and this is a snapshot of what it looks like in GeoGebra, and we're actually going to go there in just a moment. If the x value is 2, that means it's 2 years since 1970. So this would be in essence 1972. That's this a value is 1972. Okay? But it's sitting at the point 2, 32. So in 1972, there were 32 female candidates for the U.S. Congress. And then when x is 8, that would be 1978. Okay, and we had then 46, and you can see that there is an uphill climb, okay, which if you've studied history at all, relatively recent history, you'd know that that makes total sense with what was going on in our country. I'm going to bring up GeoGebra because I want to show you how GeoGebra can be so helpful with your data. I think you're going to be really pretty impressed with what it'll do. Now, I explained in a previous video about how you can access this. You simply go to www.geogebra.org. And you can also run GeoGebra into a search engine and it'll take you there. It's a totally free download, or you can work up there. And I can go through View and open up a spreadsheet, so you have other options of working with spreadsheets, but I entered my data right there. And it will go ahead and plot that data for me. Now what I'd like to do is, let me see if I can bring that over a little bit, because I'm going to, I'm going to try to go back and forth between the two of these, working with some questions and so forth. I said, first off, give the equation of the regression line from here. Okay, so what I have to do is, in essence, this. Let me bring that over here just a little bit more so that I can reach those. I select my data because along with teaching you the mathematics, I also want to show you a little bit about how to work within the software, because sometimes that's our stumbling block. And once I select that, then I have a variety of options, and one of them here allows me to do 2 variable regression analysis. Wow, how sweet is that? So I select it, and it pops up, and it's got this plot. Now I don't love this plot, but it's the same kind of thing that you'll get in some of the other applications, because you'll notice that I'm not really seeing necessarily always an X and a Y axis, but it's a plot of the data. But here's what you love. I've got a drop-down menu here for a regression model, and this is where you need to know about your parent functions, like we were practicing at the beginning of this lesson. As I look at this plotted data, do I think that it should be a logarithmic model, a polynomial, a power, an exponential? I mean, actually exponential is not terrible in that case. And what I love is you can just try them. But if you're really trying to be rather quick about it, you might just say, okay, I want to go with linear. And just like that, as soon as I select it, it is giving me the equation of that regression line, and it's running the good statistics to get that. And if you like, you can go to this options, and it will show you some statistics that goes along with this. And in fact, that R² value, you want it to be as close to 1 as possible. The closer it is to 1, the better your model is. So to 0.9889, well, that's a pretty decent model, okay? But I don't need to see that at the moment, okay? So here is my regression equation, and so it is y equals, and of course it's rounding values off. So I've got 3.5726x plus 20.8602, okay? Next question. Use that equation to predict the number of women candidates in 1984. And how well does that work? Because you know, when you get these models, they may be total trash. What you want to do is really look to see, before you try to use that model to make any big claims, you know, go out on the evening news with it or anything, you want to make sure that it is going to be an accurate model. So let's just kind of see. In 1984, let's see here, what would the x value be for 1984? Remember, the x value was the number of years since 1970. So that's going to be 14. Okay? So I say put in 14. And then I hit enter, which I forgot to do. Where's my keyboard? And actually, I think I had done it. I get a y value of 70.88. That's one of the things I love about using the technology, because if I want to find those y values, I don't have to sit and compute them. I can ask the computer to do it. That's its purpose in life, right? So I get about 71. Now, if I want to come back here and check, in 1984, there were 65. So that's actual data. And so the question is, well, how good do you think this model worked? Well, it was off a little bit. Instead of 65, it's saying about 71. And you know what I do think is interesting? Right here is that point plotted. This is your 1984 point, and you can see that it's running under the data. So you say, well, it's obviously not perfect, but it was in the ballpark. Okay, so that's my only question there. Use that same equation to predict the number of women candidates in 2008. Well, let's see here, 2008. From 1970 up to 2008, that's what, 38? So I say, okay, what if I put in a 38? Well, then I see that I'd have about 157 women candidates based upon my model. And the actual number was 139. So, was that good? Well, it was a little bit off. Okay, so we're seeing it certainly isn't a super accurate. Maybe another equation would be a little bit better model. Now, would you say that the increase in the number of women candidates has been gradual or dramatic? And I said support your answer by looking at the graph. Now, what I'd like to do here is close this graph. I may have to come back to it and just look for a moment at this guy, okay? And I'm going to do a little bit of adjusting just so we can see these points in here. Okay. What I love about this is how easy this is to interact. And what you might notice is, depending on my scale, as I set my data in this particular window, it looks like a very gradual increase in the number of women candidates. But if I simply change that scale, you can see that I've totally changed the way that it looks to me. I haven't changed the data one little bit. It is exactly the same situation. It just looks different. So you want to be careful about letting your eye tell you too much. Okay? And by the way, that's where you want to really understand what the slope is and what that's telling you. I said, what is the average rate of change for your model, and explain what that means. Well, average rate of change, you might recall, I have to go back to my graph, it has to do with slope, and it's the slope between two data points. Well, in the case of a straight line, that slope is always the same. So right here is our average rate of change, 3.57, okay? And what does that mean? What does it mean? Well, you might recall that what I have suggested for you to think about is that on my slope, I think delta y over delta x. And what was the y coordinate in this case? Well, let's see here. That y coordinate was number of candidates. So I have 3.57 candidates, female candidates, over, and the delta x is years, essentially years since 1972. So in essence, that average rate of change is saying I have about 3.5 more women candidate each year after 1970. Okay? Would you be comfortable using your model to make a prediction about the number of women candidates in the year 2108? Why or why not? Well, let's see here, 2108. Let's just see what that would look like. That's another 100 years after 2008. So if I bring my keyboard back up here, I end up with 514. Now, do I buy that? What do you think? Well, you know, one of the things I love about that particular question is there is no right or wrong answer. But what you want to do is support whichever answer you give. So I might say, well, look, it's been running high, my model has been, so I think it's probably going to continue to run high as I extrapolate out another 100 years. I think that's a reasonable comment. Somebody else can argue, well, you know, we're going to just continue to have more and more women candidates. And if you figure at least 2 candidates for every position, you know, maybe this is an acceptable value, okay? So, good news is there's no exactly correct answer. You get to justify what you believe the answer to be, okay? So, that was a chance for us to do some exploring in GeoGebra with a linear modeling problem. Okay, now we're going to go back, and what I'm trying to do is toggle back and forth between you having to do the work by yourself and you working with the technology. Because, you know, sometimes you have that technology available, sometimes you don't. So I'm trying to get both ways. Now, this was some interesting data that I came up with. This is coming from the census. And it's showing for different age groups what the median income is in 2010. And so in order to be able to plot data, what I did is I kind of took a mean age of each of those subgroups and tried to make it kind of nice. 65 and older was a hard one, so I just went to 70. And that's not a terrible one since life expectancy tends to be in the mid to upper 70s. So anyhow, I then plotted, and what you're seeing here is, this is the age, and then annual income in the year 2010, okay? And what I did like is that I didn't make up the data, and the data fell pretty much in what I thought would be a quadratic form. And since we do work with quadratic equations quite a bit in college algebra, I wanted to pull this. So I want us to use a vertex, and you can see that the vertex seems to be falling just past 46, and then it seems to be at about 64,000, okay? And then we're going to use that point, and we need one other point in order to write the equation of the parabola. So please remember our buddy the vertex form of a parabola, the vertex form of a parabolic equation. In this case, the h and k are the coordinates of the vertex. So I can nicely put those in right now. I'm going to have x minus, the x coordinate is 46, plus, and the y coordinate is 64,000. Okay? So I simply put those in. And you know, I only need to know one more quantity, this a, which is my multiplier, in order to get my whole equation. So if you think back to the days when you were in Algebra 1 in high school, and how did you find the y-intercept for an equation? you put in one point that was on the curve or on the line. So I'm going to put 30 in for X. I'm going to put 50,000 in for Y. Okay? I put those in temporarily because they have to solve this equation. And then I can find that A value. So I have 50,059 is equal to A times 30 minus 46 quantity squared plus 64,000. Okay? Then all I have to do is the arithmetic. Yeah, I didn't want to do that all in my head, so I've already got that guy ready. And there's my equation. So my A value ended up being negative 54.46. Are you cool with that value? The 54 might be hard to tell, but you know it has to be negative since that's a parabola that's opening downward. So that's at least really good news. Okay? Then I've got my equation, and I can use that equation to make predictions for other ages. Okay? And I can interpolate because I can take any value between 20 and 70. Maybe I decide, hey, what about 22 as you're graduating from college maybe, or whatever. Or I can extrapolate and go back to, say, age 14. I could go up to maybe age 80. Those would be extrapolating when I'm going outside of the data. Okay, now that was our chance to do it by hand. Now I stole a problem from our current author, Michael Sullivan, about putting fertilizer on the field and then how much yield you have. And I don't know about you guys' cornfields, but ours look awful this summer. So I've got too much data there, and I don't want to do this all by hand. I'm going to bring in the technology. And remember, I had two purposes in this lesson: to get you ready to do this by hand and to also get you ready to deal with the technology side of it. Okay, so let's slide that. Slide that. So here is a plot of my data, and you can kind of see that what happens is it is going upwards. You might almost think it's linear, but then it seems to hit a peak and fall. And that's why you would think, hey, maybe this guy is quadratic. Okay? And so, let's see. I said use the regression feature to get a quadratic function. Okay, so I come over here, and to do a regression, oops, what I need to do is select the data, okay, not the titles, just the data, and to variable, and there we go. Now I'm going to do a little bit of playing around here because we're going to do polynomial, but this is very interesting. It allows me to pick what degree I want. Well, because I'm specifically saying quadratic, because that's what we study in this course a lot, we could try a cubic. Now this is only a part of the cubic curve. You're not seeing the entire cubic, but you can see that maybe that fits the data a little bit better. And then, and there's your third degree equation, I could do a fourth degree. And I could do a fifth degree. Oh, these can get crazy. And you can do a lot of interesting investigation. I kind of like the quadratic, and I'll tell you why here as we get a little bit further along. Okay? So there's my equation, and I said, how accurately do you feel this models the data? How well can anything really model it? I think some of the other ones would model it better, but you realize that your yield on a corn crop is going to have a lot of other factors besides just fertilizer, okay? So it's probably pretty good when we're simply looking at that one factor, okay? Use that equation to find the amount of fertilizer that should be used to maximize the yield. We see these questions all the time in our algebra work, don't we? Because if you're going to have this quadratic, you know that we hit the top of the hill if it's opening downward. Okay, that's a maximum value. So I'm interested with what's going on right there. Okay? Now, how do I find a vertex? Because we call that point the vertex. You might remember that when the equation is given in standard form, that's the form that this is in, we find our x-coordinate of the vertex by doing negative b over 2a. So I say negative 1.0, I have it, 1.0765. That's the b value, okay? Negative b over 2 times a, divided by 2 times negative 0.0171. That will give me the x-coordinate of my vertex. I didn't want to do that in my head, so it ends up being 31.48. So what does that mean? Maximum occurs where x is 31.48. What is the x-coordinate in all of this? Well, if you go back and look at the table, I have a lot of layers here, that's the amount of fertilizer. So if I put on, what was that, 31.48 pounds per 100 square feet, I have got the maximum. And then the question is, well, what is that maximum yield? So in essence, I need to know how much corn I'm getting if I'm going to put on 31.48. Okay, so I'm here. Let's put in 31.48. And we find out that the maximum yield would be 20.82. And what I do like for you to be paying attention to is, what were those units? It would be 20.82 bushels for every 100 acres. Okay? One more question. What's the vertical intercept, and what does that tell us about farming? Vertical intercept. You know, some people call that the y-intercept, and this is kind of interesting in that you don't see the y-axis, so it's really hard for you to judge that just from this graph. But remember, your vertical intercept or your y-intercept happens when x is 0 and so what I want to do is I want to put a 0 in there for x. And some of you say, look, I know what that value is going to be. Good. If I put 0 in for x here and here, those get wiped out, and I get 3.89. So the question is, what does that mean? Think about the units. This is the amount of fertilizer in pounds per 100 square feet. And this is the yield in bushels per 100 square feet. So in essence, if I put no fertilizer on at all, I should be pulling in 3.89 bushels per 100 square feet. Well, you know, I think this is interesting. If I were a farmer, I'd be pondering and doing some checking on prices. Because if I put on no fertilizer and get this, how much do I make per bushel? If I put on 31.5 pounds, I'd get 20.82 bushels. How much does it cost me to buy that 31 pounds of fertilizer? How much more do I earn? Is it worth fertilizing my field? Okay, lots of interesting things in my mind to ponder. And of course, fertilizer's not the least of their worries, probably. Now, you're down at the Sale Barn Cafe having a cup of coffee with Farmer Brown and Farmer Bob, and he said you would be plumb silly to put more fertilizer on your field than that 31.48. Why? Well, I think this is actually kind of interesting to look at. If you have more than 31 pounds that you're going to put on there of your fertilizer, what happens with more than 31 pounds? As you're heading over there, what's happening to your yield? It's dropping. So you're going to spend more money to put on more fertilizer, and you're going to get less corn. So apparently, that old farmer was correct. So what do we learn out of all of this? Well, remember, I want to have you focusing on two things. Sometimes you need to write this equation yourself. And when you do, the first thing you want to do is determine which parent graph seems to fit the data the best. Okay? Then you use the features of that particular parent graph and your equation to write it. For example, on a line, find two good points and write the equation of the line through those 2 points. If it looks like a parabola would fit it better, then choose a point for the vertex and get one other point. I do suggest this vertex form is the easier way, and that's this. It's called the vertex form because you're looking right at the vertex, and then put in one other value for x and y in order to find that a value. Now, what if you're using some software, and GeoGebra is just one, there are other good options out there. First, of course, you're going to enter your data. Then, as you get it all plotted, realize that as you ask it to do a regression, it helps if you have an idea of what would fit best. Then, get your graph and your equation and be sure to consider the reasonableness and what it all means. Okay? Well, I hope you're going to enjoy working with models. I think it's a time that you really get a sense that what you're doing in algebra matters. Okay? Well, see you in another lesson.